Hello students, it's Professor Sansam. Sorry I'm not there with you today, but we're going to be doing a little bit of organic nomenclature. So to begin, I want to make sure our learning objectives are clear. Today we're going to be drawing and naming alkanes, alkenes, and alkynes, which are types of organic molecules. We'll also use line bond diagrams and learn about functional groups. So first, what is organic chemistry? Organic chemistry is the chemistry of carbon compounds. Because carbon is so flexible, being able to form between 2 and 4 bonds, it can make a huge variety of compounds with carbon as the backbone. And in fact, if you think of all of the biomolecules you're used to, carbohydrates, nucleic acids, proteins, lipids, all of them have carbon as a backbone. And as examples on the left here, we have glucose, sugar, blood sugar, ascorbic acid, which is vitamin C, and stearate, which is a type of lipid. One thing that you have to get good at when we're talking about organic molecules is how we represent them. And it turns out we have several different ways that you'll see them represented. There is the Lewis structure, which is the classic, that's on the left here. And of course it's possible to do a Lewis structure, but when you start to get a bunch of carbons in a row, they become sort of unwieldy and difficult. So sometimes we like to use a condensed structure. This is actually the condensed structure that we would use for this same molecule over here on the left. So you see the carbon on the very left has 3 hydrogens attached to it. So that's our CH3. And then we have a carbon with 2 hydrogens attached to it, and that's our CH2. And another carbon with 2 hydrogens attached to it, that's another CH2. And finally a carbon with 3 hydrogens and a carbon with 3 hydrogens, CH3. Sometimes we write this out with the bonds in the middle, or sometimes we just write them all together like this, and it's implied in this notation, this condensed structure, that these carbons are actually connected together, and then all the other stuff that's written after the carbon, like the H2 or the H3, is what's connected to that carbon. The one that's a little bit more difficult to understand is this diagram on the right. This is called a line bond structure. So each line in here represents a bond between 2 carbon atoms, with each vertex representing a carbon atom. So right here on the left, we've got a carbon atom. We have a carbon atom at that corner, and at that corner, and at that corner. Now, one of the nice things about this line bond structure is that you don't show any of the hydrogen atoms. So you just assume that there are enough hydrogens there to satisfy the valence of carbon. So for example, on the left here, where we have a carbon atom and it's connected to one other carbon atom, we know that carbon needs to make 4 bonds, so it would also have to have 3 hydrogen atoms connected to it. So we could also write CH3 here on the end to represent that. One of these carbons in the middle would have 2 hydrogens connected to it because it has to make 4 bonds, and it has 2 bonds to carbon, so it would need 2 more bonds to hydrogen. Again, in our line structure, we don't show the hydrogen atoms, so watch out for that on an exam or a problem set, because those are implied hydrogens, and you have to figure out how many there are even when you can't see them there in the structure. This molecule that we've shown you here in 3 different versions or 3 different representations is butane, a 4-carbon alkane. You can see that this is much easier if we have very large molecules to actually use the line bond structure. We only have to include things that aren't carbon, so letters rather, for things that aren't carbon. So oxygens are highlighted, sulfur or fluorine atoms are highlighted. But then we can see sort of quickly, what does this molecule look like? These are, for example, molecules of sunflower oil, and these are molecules of butterfat. Notice that in butterfat, these 2 chains, the 2 lipid chains, have 0 double bonds, and this one chain has 1 double bond, whereas over here there's lots of double bonds. Those double bonds tell us about the unsaturation. of the oil. And in fact, this is one of the reasons why butter is not as good for you, because it's a saturated fat, whereas an oil is an unsaturated fat. We also have, of course, Nasonex. Lots of pharmaceutical molecules are complex and have stereochemistry and other atoms besides carbon that are in there making a difference. Back in the day, it used to be that lard was really popular. So you can be happy too if you eat lard. It turns out lard is made mostly from stearic acid, which is actually a completely saturated lipid, whereas oleic acid is used in, or is part of olive oil. And because it's unsaturated, it actually affects the properties of the molecule. If we go back one slide, you'll see that these butter molecules, because there's no kinks in them, they're all just in a straight line, they actually will stack up right next to each other really nicely, and that makes them solid at room temperature. Whereas these molecules over here with double bonds that are unsaturated tend to have little kinks in them, and because of that, they don't stack up quite so nicely, and they'll end up being a liquid at room temperature. Okay, so if we're doing the line notation of the following molecules, remember we don't have to show anything, we don't have to show any hydrogens. We're going to have a corner or a vertex for any of our carbon atoms, and we do have to include things that are not carbon. Okay, so let's do this molecule on the bottom. I have 4 carbons in a row here. So I'm going to start with my 1 carbon right here, 2, 3, and then I have a triple bond. So between 3 and 4, I'm going to draw this triple bond. Okay, notice that's a straight line. That's because triple bonds force it to be in a straight line. And because of the way the orbitals are involved, this has to do with the valence bond theory that we learned about the other day. This would be an sp hybrid carbon there at the corner. So I've got my 4 carbons, 1, 2, 3, 4. I don't have to draw any of the hydrogens, but on this very first carbon I have 2 chlorines, so I'm going to have to draw my chlorines coming off over there. So that would be my line bond structure for this molecule. Okay, let's look at this top one. Again, we have 4 carbons, so we'll draw 1, 2, 3, 4 carbons. And on the second carbon, we have this OH alcohol group, so we'll draw our bond, and then we'll write OH, which is normally how we represent that. You could also draw O and then a bond to the H. We have to show this H because it's not an H that's bonded to carbon, it's bonded to the oxygen. So it's important to include that. Okay, so now we get to hydrocarbons. There are 4 basic types of hydrocarbons that we're going to talk about. We have alkanes, alkenes, alkynes, and aromatic hydrocarbons. Examples of these are over here on the right. Butane is an alkane. It only has single carbon-carbon bonds. Butene is an alkene, and it has a double bond. If it has double bonds, then it's an alkene. And alkynes have triple bonds in them, represented by these 3 lines. Notice this still has 4 carbons, 1 carbon, 2 carbons, 3 carbons, 4 carbons. So that triple bond has a carbon at each end of it, even though it's a straight line and not bent. Finally, we have aromatic hydrocarbons. Aromatic hydrocarbons are rings with alternating single and double bonds. They have special stability because of resonance. And benzene is really the only one that you need to know. There are lots of other names for them, and benzene is the only one that we need you to know for Chem 105. So now we're going to start getting into how we name these molecules. And you guys in Chem 105 are only responsible for naming alkanes, alkenes, and alkynes. So if there's any other kind of functional group like alcohols or aldehydes or amines, you don't need to know how to name those, just recognize the functional groups. So in terms of nomenclature, we're going to make sure to ask you questions about alkanes, alkenes, and alkynes. In any of these, there are going to be three parts to the name. There's a base that's going to tell us how many carbons we have in our longest chain. We have a suffix that tells us about which family it's in. For example, is it an alkane, alkene, or alkyne? And then we have a prefix that tells us about substituents, which are things that are sticking off of the chain, sometimes called side groups. So first we'll start talking about the base. We have this sort of prefix code word that we're going to use to talk about how many carbons there are. So for example, meth is the prefix that means we have one carbon. And if we have methane, we have one carbon and we have only single bonds, that's going to be CH4. Eth is for 2 carbons. This is ethane. Prop for 3 carbons, propane, which you might remember from a camp stove that you might have used. Butane, pentane, hexane, heptane, octane, having 8 carbons is what's the main ingredient in gasoline. And then nonane and decane. So you'll need to memorize these prefixes and which number of carbons they correspond with so that you'll be able to tell what the base of a molecule is. So butane right here, 4 carbons, octane, 8 carbons. When we're naming alkanes, the first step is that we have to find the longest chain in the molecule. And this is pretty straightforward. We're just going to look at it and count how many carbons there are. So if we look at this molecule down here, we have 1, 2, 3, 4, 5, 6 carbons in a row, and that's longer than 1, 2, 3. So the 6 carbon chain is our longest chain. And then we have a choice. We have to number the chain. Number the carbons in the chain. And we have a choice about where to start. We can start up here or we can start down here. You'll see in this example that we started up at the top and numbered it 1, 2, 3, 4, 5, 6. We did that because we want the number to be closest to any substituents. This CH3 group, a methyl group because it has 1 carbon, is a substituent, and we want the substituents to have the lowest possible numbers. And methyl, ethyl, propyl, butyl, isopropyl, and tert-butyl are the substituents that you should be familiar with in terms of naming. So if we look at the name of this molecule, we'll see that we call it hexane. Hex tells us that we've got 6 carbons in our longest chain. Ane tells us that we've got only single bonds. And then this 2-methyl tells us about the substituent. The methyl group is attached to the second carbon on the chain that we numbered. So it's 2-methylhexane. So let's name a couple of these. Let's start with this one in the top left. We're going to count our longest chain. We have 1, 2, 3, 4, 5, 6, 7 carbons. And if we went the other way, we would still have 7 carbons, so it doesn't really matter which one we choose, this top arm or this bottom arm. So we'll choose the bottom one. And we have a choice. Do we start numbering from the left or from the right? We're going to number it from the right because we want the substituent to have the lowest possible number. So we're going to call this one number 1. And we're going to call this one number 2, 3, 4, 5, 6, 7. And we know now, because we have 7 carbons and there are no double bonds, that we have heptane as our base molecule. And now we have to name this substituent. The substituent has 1, 2 carbons in it, so this is an ethyl group. And it's attached at the 3rd carbon of our chain, so we're going to call this 3-ethylheptane. That's our first molecule. Okay, let's do this one on the bottom. So this again has 1, 2, 3, 4, 5, 6, 7 carbons. 7 carbons, and so heptane is going to be our base. We have to decide where we're going to start numbering it. Now in this case, notice that if we start over here on the right, it'll be 1, 2, 3, and we get to a substituent. And if we start over here on the left, it'll be 1, 2, 3, and we also get to a substituent. So you'd think, well gosh, it doesn't matter which one I choose. But in fact, we're going to start with this one on the right. The reason being that the substituent on the right is actually bigger than the substituent on the left, and so it's more important, and we want it to have a lower number. So again, we start over here with carbon 1, 2, 3, 4, 5, 6, 7. We've got our heptane, and we've got two things that we have to talk about. There's this ethyl group here, and there's a methyl group here. So this is a 3-ethyl, and this is a 5-methyl. Now, when we put these in our name of our compound, another rule exists. We don't list them by their numbers, although in this case it works out that way. We don't list them by their numbers, we actually list them in alphabetical order. So ethyl will come first, and we'll have 3-ethyl, 5-methyl heptane. Notice it's 3-ethyl -5-methyl heptane. There's no space here. I just didn't have perfect writing to make it match up. I'll leave the other two here for you guys to practice on your own. Next we'll talk about alkenes. Alkenes are very similar to alkynes, except they're going to have a double bond. The only thing that really changes here is that when we choose the longest chain must include the double bond. So if we look at this molecule on the left, we have a longer chain, 1, 2, 3, 4, 5, 6, 7, 8, but it doesn't include the double bond, so we have to include this part of the chain, 1, 2, 3, 4, 5, 6, 7. Even though it's shorter because it includes the double bond, we count that as the longest chain, or our base of our molecule. Now, when we're numbering our longest chain, we have a choice to start up here or to start over here on the right. And this time, we want to make sure that the double bond has the lowest possible number. So we'll start over here at the top. This is 1, 2, 3, 4, 5, 6, 7. So this is going to be a heptene. A heptene molecule. And we have to tell the people we're talking to where the double bond begins. And you'll see the double bond stretches between carbon 2 and 3. So we're going to put a 2 here to tell them that double bond starts at the second carbon. We also have to name this substituent because it has 3 carbons, 1, 2, 3. That's a propyl group. And it's attached at the third carbon, so this will be 3 propyl, 2 heptene. Okay, I'll leave that other one for you guys to practice on your own. Finally, we have alkynes, and alkynes are going to have at least one triple bond, carbon-carbon triple bond. They're unsaturated because they have that triple bond. So the more double and triple bonds you have in a molecule, the more unsaturated it is. And the process is analogous to what we did for alkenes, except we're going to end with -ine to indicate that we have a triple bond. So we'll identify the longest chain that includes the triple bond. In this molecule, 1, 2, 3, 4, 5 carbons. We'll start numbering it over here because that's closest to where the triple bond is. So this one would be 2 pentyne. And we need to talk about this substituent. It's a methyl group and it's on the 4th carbon, so that's 4-methyl 2-pentyne. I'll leave the other one for you guys to practice. Finally, we have aromatic hydrocarbons. Mostly you just need to memorize what these look like, and benzene is the only one that we really need you to know. You could call it an aromatic group if it was attached to another part of a molecule, or you can call it benzene. It's especially stable because of resonance between these two resonance structures, and so it's less reactive than similar alkenes because of that. Okay, we also have several functional groups, and these are, as the name suggests, groups of atoms that give molecules a certain reactivity. So anything that's not an alkane, for our purposes, is going to be called a functional group. So on this chart from your textbook, it shows you all of the functional groups that you guys need to know for your exam. In particular, you want to be able to recognize them. And you want to recognize them in a variety of contexts. For example, this is a sort of a line bond drawing. This is more like a Lewis structure. This is a ball and stick model. Any of those are possible as ways that we could show it to you, and you have to be able to recognize that functional group. So we start with alkene and alkyne, which you guys have already seen. We have alcohols that have OH groups, where the OH is attached to a carbon. And an example is methanol. We have ethers, where you have an oxygen atom that's between two carbon atoms. So it's called an ether. And we'll talk about actually all of these guys in the next couple of slides. So I won't go into more detail here. Just know that these are all the ones that you need to know, and you need to be able to recognize them, circle all of the atoms in the functional group, etc. So first, alcohols, they're going to have a hydroxyl group or an alcohol group. We often represent this with R and then the OH, where R means the rest of the molecule. If you were circling this functional group on a molecule, you would circle the OH part of it, and you wouldn't circle the rest of it. These are some examples down here. If you have carbonyl-based functional groups, these are going to include aldehydes and ketones. Aldehydes are on the hide of the molecule, meaning the end of the molecule. So you'll see a carbon double bonded to an oxygen, and it'll be connected to another carbon on one side, but then on the other side there's just a hydrogen atom. And that's not shown in our line bond drawing. That's an aldehyde. You can also have a ketone. Ketones have the C double bond O, but that carbon is connected to carbons on either side. So that's our ketone group. Carboxylic acids are related because they have a C double bond O, but instead of being connected to a carbon on both sides, or a carbon on one side and a hydrogen on the other, like the ketone and the aldehyde respectively, this C double bond O is connected to an OH group. So it's sort of like a combination of a ketone or an aldehyde and an alcohol group, but it has a totally different functionality. This makes things acidic. And so these are common acidic molecules. You've seen this before. If you think about acetic acid, we said that it was CH3COOH. This COOH is this functional group carboxylic acid. Butanoic acid, as a matter of interest, is the molecule that's responsible for the aftertaste of human vomit. That's a great thing you wanted to know about, right? I thought so. You're familiar with lots of these from foods. We tend to eat foods that have weak acids, like these carboxylic acids in them, citric acid, acetic acid in vinegar, ascorbic acid in vitamin C, etc. Amines. Amines are organic bases, and the nitrogen lone pair is reactive, so they tend to have really strong odors. For example, nicotine, capsaicin is responsible for your hot peppers the heat in hot peppers. Caffeine is an example. Anytime that you have a nitrogen, it can be bonded like this one to 3 other carbons. It could be like this one where it's attached to 2 carbons and a hydrogen, and sometimes you just have an NH2 where it's only attached to 1 carbon. All of those are amines. We also have something that's called an amide. Now, an amide is formed by the reaction of carboxylic acids with amines, and so it looks kind of like both of them. You have a C double bond O, like you would have from the carboxylic acid, and then you have an NH. So the C in your C double bond O is actually connected to an N on one side, and this is called an amide. So that's our amide functional group. These are extraordinarily common in biomolecules, for example, amino acids. Amino acids are called amino acids because they have an amino group on one side and an acid group on the other. I think the bonds kind of got erased here, but this would be, one amino acid molecule. This is another amino acid molecule. And of course, amino acids are what go into proteins. So how does this work? It turns out the OH from our carboxylic acid and the H from our amine get together and make water. And now we have a new amide bond. Beautiful artwork too, don't you see? Okay, so notice our carbon over here from the acid group is going to be connected to the N from the amino group when this water leaves. And we get this new amide bond. And if we were circling this, we'd have this C double bond O, NH. I should include the NH there. C double bond O, NH as our amide functional group. And in the case of proteins, because amino acids go into proteins, we sometimes call this a peptide bond, which you probably have heard of before. Notice that peptide bonds are actually amide functional groups, C double bond O and H, and we call that the peptide bond. So this is what happens when we build proteins from amino acids. Okay, we've got ethers. They tend to be pretty unreactive. You might have heard of ethers before because they can be used like in old movies. They'll use ether to knock someone out. Diethyl ether is my favorite ether because it looks like a little bat. So our oxygen here in our ether functional group is connected to a carbon on both sides. Just an oxygen with a carbon on both sides, that's an ether functional group. We also have esters. Esters are from the reaction between carboxylic acids and alcohols. Similar to the formation of an amide bond, the OH and the H go away, and we now have a C double bond O, and that C is connected to an O on one side. And the O is connected to another carbon. So this is a sort of way to link 2 carbon chains together. This one's called an ester, and it's commonly found, these are smelly, so they're found in lots of fruits and perfumes and things like that. Propylbutyrate over here on the left is actually the molecule that they use in as like a pineapple scent. So if you have pineapple lotion, you probably have propylbutyrate added to your pineapple lotion to make it have that scent. Notice though, this is from propyl alcohol and butyric acid. And if you remember, butyric acid is that molecule in human vomit. It also smells sort of like rotten butter. So if your pineapple lotion sits around for too long, it might decompose and reform that butyric acid, and then it will not smell quite so pleasant. Okay, we've reached the end of our presentation on organic nomenclature. I hope it's been helpful and you've learned a lot. The TAs will be here to answer your questions. Thanks, goodbye.